In the following circuit, the EMF of battery 1 is 2.00 volts. Battery 2 has an EMF of 4.00 volts. Resistor 1 has a resistance of 2.00 ohms, and resistor 2 has a resistance of 1.00 ohms. What is the magnitude and direction of the current in each resistor? What is the potential difference across resistor 2? So in this problem, we have two power supplies, two batteries, with different amounts of voltage across their terminals. Now, these two batteries are driving current that will go across three different resistors. A couple of things to note about this problem is that we have essentially three branches that are each in parallel with each other. And we could see that by just labeling a couple of points. If we call this point A, and let's just go around the circle. So we'll call this point B, point C, and point D. We see that we have branches, a branch going from A to C, going from A to C through battery 1, A to C through the resistor 2, and A to C through battery 2. We're going to use this to help guide us in solving this problem. So let's go ahead and redraw this circuit. We have three components that are in parallel. The first component has battery 1 and a resistor. We will label this psi 1 for the EMF of battery 1 and R1 for the resistance of resistor 1. So the EMF of battery 1 was given as 2.00 volts. The resistance of resistor 1 is given as 2.00 ohms. This series combination of battery 1 and resistor 1 is in parallel with resistor 2. Resistor 2 has a resistance of 1 ohms. And let's notice that resistor 1 has twice the resistance of resistor 2. So let's express resistance 1 as a multiple of the resistance of resistor 2, which I'll now relabel as R. So that means resistor 1 has a resistance of 2R. This will reduce the number of unknowns we have to work with, or the number of variables, rather, we have to work with. And we see that these two branches are in series with the second battery and a third resistor. Second battery has an EMF of psi 2. That is given as 4.00 volts. Notice the EMF of battery 2 is twice the EMF of battery 1. So let's express it as a multiple of the EMF of battery 1. So let's express it as 2 times psi, where I'm relabeling the EMF of battery 1 as just psi. And as stated, these three branches are in parallel with each other, where we are calling this point A, and we have called this point C. And let's go ahead and label the other point. We had called that point B and this point D. Our goal is to determine the magnitude and direction of the current in each resistor. So in other words, how much current is moving through each resistor and in what direction that it's moving. And once we do that, we have to determine the voltage across resistor 2. So for circuit problems, if we don't know the direction of current, that's okay, because we're going to use Kirchoff's laws. Kirchoff's laws will help us determine the current and the current direction. But what we have to do is we have to assume a direction for the current. So that's going to be the first step that we're going to do. Assume I, and that's the direction for the current, in each branch. So you're saying, well, how do I know what to assume? That's okay. As long as we are consistent with our assumptions, then we will end up getting the value for the current. And if the value for current that we get is actually a negative number, all that means is the actual direction of current is opposite the direction we assumed. Its magnitude will remain the same. So here, let's go ahead and assume that the current in the branch going through battery 1, we'll assume the current goes through from the negative to positive terminal of battery 1. Let's go ahead and call this current 1. I like to start off with assuming the currents for the branches that contain the batteries. So now let's look at the current for battery through the branch that contains battery 2. Let's assume the current goes from the negative to the positive terminal of battery 2. I will call this current 2. And notice those two currents are going into branch C. Let's label that. Let's label that relationship. We will say I1 plus I2. And remember from Kirchhoff's laws, current into a node must equal to the current coming out of the node. So if currents 1 and 2 are going into node C, then there must be a current coming out of node C. And that current we will call current I3. And so the sum of currents I1 and I2 must be equal to current I3. So this is applying one of Kirchhoff's rules. Current into a node must equal to a current out of a node, or a current into a branch must equal to a current out of a branch. Now that we have chosen the direction of currents, we now have to choose the direction of. Now that we have chosen current direction, let's choose the loops in which we will evaluate the voltage. We need to choose independent loops. So let's write that down. Choose independent loops for adding up the sum of potential differences in a loop to be equal to 0. Now remember, an independent loop is a loop that has at least one branch that is not contained in any other loop. So for example, let's look at loops beginning and ending at point A. So one loop beginning and ending at point A goes all the way around the circuit. It goes through battery 1, all the way around, going through battery 2. We could call this loop loop 1. Let's look at another loop. Let's look at a loop that only goes through battery 1 and resistor 2. So this loop that goes only through battery 1 and resistor 2, we will call loop 2. And now let's look at a loop that only goes through battery 2 and resistor 2. So this loop right here, we will call loop 3. So notice we have 3 loops, but only one of them is independent. So what this means for us is we're going to need to decide which 2 loops to use, because if we use all 3, all the third loop will tell us is a true statement, something like 7 equals 7. A true statement is good because that means we didn't make any mistakes, but a true statement like this wouldn't necessarily give us any additional information that we didn't already have. So out of these 3 loops, only 2 are going to be independent. And how do we know which 2 are going to be independent? Let's choose 2. And then the third one we'll see can't be expressed in terms of, the third one we'll see will not have a loop that isn't a part of any other loop. Let's look at loop 1. Let's just propose that loop 1 is one of our independent loops. So for loop 1 contains the branch from A to C, going through battery 1, and it contains the branch from C back to A, going through battery 2. Okay, so let's look at loop 2. Loop 2 goes from A to C back to A. So let's see, A to C back to A, going through battery 1 and resistor 2. Let's look at loop 3. Loop 3 goes from, well, let's see, it goes from A to C to A, traveling through battery 2 and resistor 2. So if we choose loop 1 as one of our independent loops, notice how it contains both batteries, but not resistor 2. If we look at loop 2 as one of our independent loops, it contains one battery and resistor 2. So let's look at what we have. Loop 1 contains both batteries. Loop 2 contains one battery, battery 1 and resistor 2. And loop 3 contains battery 2. And notice battery 2 is already contained in loop 1. And loop 3 contains resistor 2. And notice resistor 2 is already contained in loop 2. So we would say if we choose loops 1 and 2 as our independent loops, then we won't use loop 3. Now my choice to begin was arbitrary. We could use loops 2 and 3 as our independent loops, and that would mean that loop 1 would be dependent. Or we could choose loops 1 and 3 as our independent loops, and loop 2 would be dependent. In other words, let's only choose 2 loops, and it doesn't matter which 2 loops we choose. So for our independent loops, I am going to choose loops 1 and 2. And in doing loops 1 and 2, we're going to apply Kirchhoff's law for voltage in a complete loop. So in other words, we're going to sum up all of the voltages for a complete loop.